Welcome to the Introduction to Exponential Growth and Decay podcast. So I have a little anticipatory problem for us. Excuse me. So according to legend, the inventor of the game of chess requested payment as follows. My request is a modest one. I humbly request 1 grain of rice on the first square of the chessboard, 2 grains of rice on the second square, 4 grains of rice on the third square, and so on. Each square represents twice as many grains as the previous one. The king agreed to the request immediately without doing any calculations. Do you think this was wise? So now let's think about this problem. What's going to happen as we go to every single square on the chessboard? Right? What's happening if we're having twice as many? Right? We're going to keep doubling, right? We're going to keep doubling the amount of rice. So we're going to be doubling the amount of rice for each square. Now, if you think of how many squares are on a chessboard, right? We're going to be doubling it 64 times. That's a lot of doubling. Right? Without even figuring out how many that is, that seems like that's going to be a lot of rice. Let's see how much rice that is. And let's see if we can write an equation for it. All right, so on the first square, we have 1 grain of rice. So that's 2 to the 0 power, right? Because anything to the 0 power is 1. On the second day, we have 2 grains of rice. Well, 2 grains is the same as 2 to the first power. On the third day, we have 4 grains of rice, and 4 grains is the same as 2 squared. So let's figure out each day. So now on the fourth day, notice the pattern here. We're doubling our rice, right? So now we're going to have 8 pieces of rice. Well, that's the same as 2 cubed. And then the next day, we're going to have twice as much, not the next day. The next square, we're going to have twice as much rice. So now on that square, we got 16 grains of rice. Well, that's the same as 2 to the fourth. And on the sixth square, we're going to have twice as much as the fifth one. So we're going to have 32. And that's the same as 2 to the fifth. Now, I don't want to have to do this for 64 squares. That's going to take us a long time. This podcast can only be so long. All right, so we want to write an expression for the number of grains on square X of the chessboard. And if you want to impress me, before I go over, maybe pause it, and you write it on your notes what you think it is. And let's see if it matches mine. Right? So if you match mine all on your own, that'll impress me. All right, so if you want to write it down, you can pause the tape, write it down, because now I'm going to go over the answer. So we're going to write an expression for the number of grains on square X of the chessboard. I hope that you noticed that this is just like our geometric sequences. Right? So the amount of rice on any square, right, we started off, right, with how much rice did we start off with? Right? We started off with 1 grain of rice. And what are we doing each time? Well, we are doubling it. And so that means our ratio is going to be 2. Right? So our first term in our sequence here is 1. And our ratio is 2. Right? Now, let's see if we can figure out the exponent. Well, let's take a look and compare. So on the second square, for instance, we have 2 to the first power. On the third square, 2 squared. On the fourth, 2 cubed. I think you can see a pattern here that the exponent is 1 less than the square. Let's see if this works out. Let's see if we plug in the numbers if we get the right thing. All right, so on the first day, right, we would have, I'll just put it over here. So A1 would be 1 times 2 to the 1 minus 1. So that's 1 times 2 to the 0 power. Anything to the 0 power except for 0, which has no meaning, would be 1. And then 1 times 1, of course, is 1. Well, that matches up. How about on the second day? All right, so 1 times 2 to the, now we have 2. 2 minus 1 power, and that would be the same as 2 to the first power, or 2. Well, that seems to be correct. Right? I can keep on going like this, and it seems like it matches our pattern here. So that would be 2 squared, which is going to be 4. And notice that equation matches what we have in our table there. All right, so that looks pretty good. All right, so now we want to figure out, probably should move all this stuff over here where I had lots of space. We want to figure out how many grains of rice are going to be on the 64th square. Now we're not figuring out all the rice all together, right? We're only figuring out the 64th square, because each one of these numbers represents how much is on one square. So if we want to find the 60, the whole total here, that we're going to have to add up all our squares. And we're not going to do that. But let's just see how much is on the 64th square. Actually, I'm going to move this last little one. Will the whole thing move? No, but most of it will move. So I hope you've enjoyed watching me move these over where it's less crowded and you can actually see what I wrote down. There we go. All right, so let's calculate out the 64th square. So we'd have where are we going to solve it? Over here, I guess. I'll do it over here. So we have A64 is 1 times 2 to the 64 minus 1 power. So I'm going to put that into our my calculator. I'm not going to do that in my head. So 1 times 2 to the 63rd power. And that is going to be, and hopefully my calculator won't mind, so 2 to the 63rd power is, well, put it in exponential form, or in scientific notation, I should say, because it didn't really like the number. So let me see if I can write this down for you. So we have, put it over here, so I don't have to bend over the whole time. 9, 2, 2, 3, 3, 7, 2, 0, 3, 7, and then it says times 10, it says E18, which means times 10 to the 18th power. So if I move the decimal place 1, 2, 3, 4, 5, 6, 7, 8, 9, I have to add 1, 2, 3, 4, 5, 6, 7, 8, 9 more zeros there to get how much rice is on the, on the 64th square. Right? I don't even know what that number would be, because it's, we've got the first 3 are hundreds, and then thousands, and then millions, and then billions, and then trillions, and then quadrillions, and then quintillions. Right? So that's a whole lot of rice. I don't even know how I was going to fit that on that square. That's how much rice would be on that 64th square. Well, I hope one thing you figured out is, number one, that our amount increases by a common ratio. Right? We have a common multiple, something we're multiplying by each time. And number two, how quickly exponential functions grow. Right? They grow very large very quickly. Let's take a look at exponential functions. Whoops, for some reason we have this one twice. And moving along. Any day now. There we go. Why do we need this? So most situations that people study do not have linear relationships. Population growth is now heavily studied around the world. And is this a linear function? It is not. It is not a linear function. People don't grow at a constant rate. This is actually an exponential function. Why would people want to study population growth? Things like, so why study population growth? And you can think of many more reasons than I write down. Making sure there's enough resources in an area, perhaps, for the population. Or as the population grows, right? Usually we have to have the resources there in advance, or know what the population is going to be, so we can have the resources at a later time. So enough resources for an area. Things like building schools, if we know how the population is growing, we'll know how many schools we might need. Okay. Concerns about overcrowding, maybe in certain cities. Okay. Having enough food. Food and water. For an area or for the whole world. Right? So lots and lots of reasons to study population growth. And we don't have to study just population growth of people. It could be of animals. Is a species endangered? Or is an endangered species making a comeback? What's the population of a species, right? So lots and lots of reasons. I just wrote down a few there. There's many, many more. So we've looked at linear growth where the amount of change is constant. Here we have a graph of the amount of money your parents give you based on the number of A's that you receive on your report card. So if you get, for every A you get, your parents are going to give you $10. Can we easily predict what you would get if you had 7 A's? Well, if you get $10 for every A, you should have $70, right? Pretty simple. So what equation would represent this situation? Well, what happens if you get no A's? No A's. Well, you get no money. Right? So you're not going to get anything for 0 A's, so you're not starting off with some money. Your parents aren't going to give you money just because you got a report card, right? You got to get an A on it. So the equation that would represent this situation here is $7 for every A, right? So now let's take a look at here's a linear situation. Let's take a look at a very similar problem, but let's make it exponential. So what if you asked your parents to reduce the amount per A to $3? $3 is enough for me. You can just give me $3. But then ask them to use the following function, right? So you can just give me $3 per A, but I don't like that other equation. I like this equation instead. So let's graph this and see. All right, let's get a table of values here. So what if you got 0 A's? All right, so 3 to the 0 power is 1. You still get $1 even if you get 0 A's. What happens if you get 1 A? 3 to the first power is going to give you 3. So if you're only going to get 1 A, you were better off getting $7 per A. The other function was better. But what if you get 2 A's? All right, so now you get $9. Well, you were still better with the other one. You were getting $10 before, so you would have gotten $20. So if you only had 2 A's, then perhaps you should choose the other function. But what if you get 3 A's? Now you got $27. It's getting a little closer. You were still better with 30, but it's getting closer. What happens if you can get 4 A's? You're going to work really, really hard. And put my 4 in the wrong spot there. And you're going to get 4 A's. Well, 3 to the 4th power is $81. Well, if you can get 4 A's, this is a much better function. What if you can get 5 A's? So 3 to the 5th power. That's going to give you $243. And how about 6 A's? That's going to give you $729. Well, I have no room for the 7th A. Whoops. It's going to move everybody up. Will it all move up? Pretty good. Sort of. Move everybody up. Up, up, up. We need to assess a little bit of space for that 7th A. Come on, 7th A. I should plan my writing better. Come on, move up, move up. There we go. Well, the 7th A, so that's going to be 3 to the 7th power, and that's going to be $2,187. Just wanted to double check that number. So these are all, of course, dollars. All right, so you're going to do really well. You'd do a little bit better if you got no A's for choosing this equation. And as soon as you get 4 more A's, look at how great you're doing. That would really inspire you to get 7 A's. Right? You're not even taking 7 classes. Somebody will find a way to get 7 A's, right? So here it is graphed, and so it's kind of hard to graph these first couple values because for 0 here, I'm at 1. And my boxes here are going up by 10. So I guess maybe right here. And for that first A, I'm going to get $3. Well, that's not very much more. For the second A, things are looking up. I'm going to get $9. For the third A, all the way up to $27. Then for the fourth A, we're going to get $81 right here. Well, if you make it not big enough, it'll be in the right spot. And then for the fifth A, $243. And I didn't even bother to try and graph anything beyond that. So here, you can just see by the fifth A alone here, look how fast that's growing. And I didn't mean to curve outward. I just couldn't see where my last point was when I was drawing this. Here we go. Whew. So you can see how much faster the exponential functions grow than our linear functions. They go much faster. They start off slow, right? My line would have had a steeper slope than my exponential function for anything less than 4. But after that, it goes much, much faster. And you never get $0. So not a bad function if you're going to get more A's. So there are many quantities that grow exponentially. Some examples are population and compound interest. And understanding of exponential growth is essential if you want to be comfortably rich later on. The special thing about exponential growth is that the rate of growth increases as time increases. We can see this in the graph at right. So the curve gets steeper and steeper as time goes on, right? And this graph here, this is only nice. This isn't even that much interest, only 8% interest, right? But look at how much it grows from 1,000 to 5,000. So we can see that that's much faster than if it was just a line. Right, so an exponential function, a function is called an exponential function if it has a constant growth factor, so constant ratio. So our geometric sequences model exponential growth. I had blanks in your notes and I forgot to mention them, and you might have missed it. So at the very top of the page, fill in the blanks there, right? And they're basically all underlined there. The special thing about exponential growth is that the rate of growth increases as time increases. So right in that underlined part there, and the curve gets steeper as time goes on. If you need to, pause the tape, all right? So I can go on. The last thing I want you to do in your notes is write down that right over here, geometric sequences model exponential growth, right? So for a fixed change in x, y gets multiplied by a fixed amount. So example, money accumulating in a bank at a fixed rate of interest increases exponentially, right? So we're going to be multiplying by some ratio each time. I'm going to end this podcast and I'm going to pick up because I just barely got into this topic, all right? So and mostly you just had to listen to me. I hardly had to write down anything. So I'm going to do one more podcast so this isn't too long, and I'm going to pick up in the notes. All right, so I'll just pick up where I left off. See you in the next podcast.